Hello everyone, and thank you for taking the time to visit my poster. Today I will be presenting our research on optimizing porous lattice structures for additive manufacturing in high performance engineering applications, with a focus on how different porous geometries influence mechanical and microstructural properties. The core idea behind this project is to explore how engineered porosity can be used to reduce weight and enhance performance in components, particularly in aerospace applications, where weight is a critical design factor. We specifically used Inconel 718, a nickel-based superalloy, which is widely known for its excellent strength, corrosion resistance, and high temperature performance. In traditional manufacturing, producing complex porous structures is either extremely difficult or outright impossible. But additive manufacturing and laser powder bed fusion, or LPBF in particular, has opened up new possibilities. With LPBF, we can fabricate intricate 3D lattice structures by melting layers of powder using a high-powered laser, giving us full control over the internal architecture of the component. This study focused on several types of porous geometries. We included BCC, FCC, which correspond to body center cubic or face center cubic, and their Z strut variants. We call them BCCZ, FCCZ, as well as triply periodic minimal surface structures like gyroid, diamond, and Schwartz. All samples were designed with a 45% porosity level and fabricated using a EOS M290 LPBF machine under carefully optimized parameters. The laser operated at 285 watts with a layer thickness of 40 microns and a scan speed of 960 millimeters per second. After fabrication, the samples were tested mechanically and analyzed macroscopically. We conducted uniaxial compression tests using a Shimatsu testing machine and performed Vickers hardness measurements. Across 16-point grids, we also conducted scanning electron microscopy both before and after testing to observe microstructural features like melt pools, grain structures, and defects. Now, let's talk about the results. Among the lattice structures, FCCZ showed the highest yield strength at 965 megapascal, followed by BCCZ at 946 megapascal. These Z strut variants clearly offered improved mechanical resistance because the vertical Z struts enhance load-bearing capacity. On the other hand, the gyroid and diamond structures, which belong to the TPMS family, showed greater ductility and energy absorption. The gyroid, for instance, experienced the highest compressive displacement, around 4.8 millimeters, making it a great candidate for applications where flexibility and energy dissipation are more important than raw strain. In terms of hardness, the diamond structure exhibited the highest value, about 421 HV, while gyroid had the lowest at 337. These results highlight the trade-offs between hardness and deformability in different porous architectures. Also, we did FEA analysis, and based on FEA analysis, we saw the stress distribution is for different porous structures, and we compared the values for stress concentration using different porous structures, and we saw the FCC material is has less local strain than the BCC structures. So, based on these results, moving forward, we plan to explore fatigue testing and anisotropic behavior under cyclic loading to further refine our understanding. We are also interested in examine how scan strategies and post-processing methods affect microstructure performance. This project not only demonstrates the power of additive manufacturing but also aligns with broader goals of developing lightweight, high performance, and geometrically optimized components for critical industries. Thank you so much for your attention. I would be happy if you put any comments for, if you have any question, you can, ask within the comments below. Thanks for your attention.